Continuing to our discussion on moles, we want to look at how moles interact with some of the ratios, especially related by molecular formulas that we talked about earlier on. So when we're dealing with conversion factors related to counting units or related to numbers of objects, it doesn't matter how we are counting, those ratios are all still going to be the same. So we'll stick with our bakery examples. Say you're making an Oreo donut, and for every one donut, you need 2 Oreos. So 2 Oreos for every 1 donut. These right here are descriptions in pure counts, not counting units, just counts. I'm counting 1 donut and then 1, 2 Oreos. If I turn it into a counting unit representation, where now I have dozen, that's a group, and dozen, a similar group, the exact same type of group, my ratio is the same. It was 2 to 1 and 2 to 1. And you will note the only thing that is different is that I'm counting by groups. And I need to count both things by group, but importantly, the numbers stay the same, whether or not you're counting individual objects or you're using the counting units and counting by groups. Those ratios are locked in. So if I turn it to a molecular world, where say I look at water, so I have, say, H2O, my molecular formula is over here. And if I have H2O, I could have my structural formula. It's 1 oxygen and 2 hydrogen atoms, so similar to my donuts, or Oreos. I had two hydrogens for every 1. And again, these have different names, but these are still individual counting an object, individual objects, right? 1 molecule, 2 atoms. If I instead turn that into a counting unit, I still can see the numbers stay the same. It's still 1 to 2, but now it is a dozen water molecules and 2 dozen hydrogen atoms. But importantly, 1, 2, 1, 2. Okay, so those stay consistent. I could use, this is true for any counting unit that I potentially have. So I could bump it up to moles, and I could see that 1 mole of water is 2 moles of hydrogen atoms. We can see that this 2 that we're looking at right here comes from the molecular formula. Sorry, that's a little bad. It comes from the molecular formula that we're looking at. And so that number, we can use that number. Previously, when we started looking at molecular formulas, we just were doing this sort of representation where we were looking at molecules and atoms. But we can use the same analysis to identify moles of atoms in a mole of molecules, or moles of compound, whatever it is. Let's take a look at an example. How many moles of sulfide ions are contained in 1.7 moles Al2S3, aluminum sulfide? I just want to start by asking, what do we want? How many moles of sulfide ions? Okay, so sulfide ions, we know that aluminum is a metal. Aluminum is a metal, so this aluminum sulfide is ionic. So the sulfur in there is not an atom. It's not a neutral atom. Those are sulfide ions, anions, because the aluminum is a metal, so it has to be a cation. So we're basically just asking for, and this is similar to, they're not quite, we've used atoms in the previous examples, which is a little bit different because we're dealing with an ionic compound. But again, we want moles of sulfide ions. So we can look at sulfide ions. That is a component of the compound, and we're going to count them by groups. We're going to count them in moles, not individual objects. What information do we have? We are given information on the moles of compound. Okay? So if we want to think about how we can relate these, we can start to see, well, moles is what we want. That's counting by group. We have information on moles counting by group. Okay, so we don't need to change that. We're not going to use Avogadro's number here. What we're trying to relate is the relationship between ions and the compound that they're contained in. So what we're really trying to change is, again, what we're counting. not how we're counting it. We're counting it by group in both cases. We just want to change what we're counting. And so that's where our molecular formula is going to come in. The molecular formula lets us change what we are counting. Is it the whole compound or is it those component ions? In this case, the component sulfide ions. So let's work that out, see how it goes. How many moles of sulfide ions are contained in 1.7 moles Al2S3? Right, so what we're after is moles of sulfide ions. And what we have is 1.7 moles of the compound. This would be similar to asking moles of atoms. They're just ions because that's an ionic compound. Aluminum's a metal, sulfur's a nonmetal, and sulfide is 2 minus. And so really what we're looking at is we're going from moles of Al2S3 to moles of sulfide. Let's write that out. Okay, and we can see we want to get rid of moles of Al2S3 and go to moles of sulfide. Those units would cancel out to give us what we wanted. And so this is moles of Al2S3. This is still moles of S2 minus. So moles to moles, we're not changing those. We're counting by groups. We're counting by groups. What we're changing is just what we are counting. Are we counting Al2S3, where that's a compound that has multiple atoms in each package, or are we counting individual ions? So we see that previously we would have said that our definition would have been that one, this time it'd be a formula unit, but similar to a molecule because it's ionic, of Al2S3 contains 3 S2 minus ions, right, where this 3 comes from right there in the molecular formula. So that's similar to what we did in an earlier example. And that relationship is true. But now we're dealing with moles. So instead of one formula unit, we want 1 mole Al2S3. And that's still going to be equal to the same 3 moles of S2 minus. The 3 is the same 3 we had right there. The only difference is now I'm dealing with mole. And you could do this in any formula unit or any counting unit that you wanted. This, you're counting individual objects. Here, you're counting by groups, as long as you're consistent. You can't have mole ions, but you can have mole or formula unit ions, as long as you are consistent there with how they're paired up. So we can take these numbers. The 3 goes next to the moles of S2 minus. The 1 goes next to the moles right there. So 1.7 times 3 divided by 1 gives me 5.1 moles of S2 minus. All right, so let's put this idea of ratios with the earlier ideas we talked about defining the mole. How many oxygen atoms are there in 2.3 moles of O2? Starting off, what do we want? How many O atoms? So we can see we're counting O atoms, and we're counting atoms, not moles. These aren't groups. I want a total count. Information given, moles of O2. So see the information that we are given is the fact that we're dealing with moles of O2. We're going to think about how we relate these. The first thing we can see is that there's a couple differences. We always want to be looking at what are the differences. Oxygen atoms, we can see, have the formula O. That's just single O, and we're trying to get in to O2 molecules, or we have the information already in O2 molecules. So one of our differences we can see right away is it's subtle, but we are counting different things. We're counting in one case oxygen atoms, and in the other case oxygen molecules. So that is where the molecular formula comes in. The other difference that we're looking at is in one case, this is a total count of objects. We want total oxygen atoms. We are counting molecules by groups. So there are two differences we're going to need to deal with. One is the idea of what we are counting, either molecules or atoms. The molecular formula is what allows you to change that. Molecular formula lets you change what you are counting. Then we want to change how we're counting it, either by group or by individual object, and Avogadro's number is what lets us do that. Before we work out, let's go ahead and take a look kind of graphically. We kind of talked about this. I mentioned this earlier. This is a tricky thing. So when we're dealing with moles of O2, right, we are counting these molecules. You're counting whatever that formula is, O2 molecules. So those are, we can see that's what we are counting. But when we're asked for atoms, that's a different thing that we're counting. It would look like that and that. I want to count each of those, right? I want to count each individual atom. I don't care how the atoms are paired together. I just want to know how many total atoms I have. And so that's why it can't just be converting from moles into molecules. We have to do another step of going between molecules and their component atoms. All right, so hopefully we'll take a look, work this out, and see what we get. How many O atoms are there in 2.3 moles of O2? All right, so I want O atoms, starting with moles of O2. So when we look at this, you can see that we have a couple differences between where we're starting and where we're ending. .3 mole O2, and in the end, I want O atoms. We've seen that there's a couple differences here. One, O2 versus O. Those are different molecular or different formulas, implying that they are different substances. We have moles and atoms, counting by groups, counting individual objects. So we have two differences between where we're starting and where we're ending, and we're going to need to account for both of those. Okay. So the first thing we're going to do is we're going to deal with this group concern. I'm in moles and I want to go to atoms. So I can't directly do that because these are moles of molecules, but I can certainly step down from counting groups of molecules to counting individual molecules. I know that in 1 mole of O2, there's 6.022 times 10 to the 23rd molecules. Not straight across here, but we're doing all right. And so we can see that that takes care of the fact that I was counting in groups. I should note, I forgot to write it. It's still molecules of O2. Sneak it in there. So we're still dealing with molecules of O2. We've only changed how we are counting the O2, by group or by individual molecule, one at a time. So now I need to take care of the fact that I want to go from molecules of O2 to O atoms. And I know that it's going to be 2 O atoms for every 1 molecule. Right? That 2 comes from right there. Right? The fact that it's a 2 in the molecular formula, I cancel out molecules of O2, giving me O atoms. I'm going to rewrite this for some extra space, all down here. I end up with 2.8 times 10 to the 24th O atoms. It's nice for working through the problem, but not quite space. Thought I could leave myself enough, but still ran out. Avogadro's number really gets in the way. And so we can see when we're working through this, these parts that we've used are still the things that we were using previously. We've just joined them together. This is still Avogadro's number, and this still comes from the molecular formula. So those are the same conversion factors we saw. Avogadro's number lets you change, are you counting by group, counting individual? Molecular formula, are you counting the molecule as a whole or individual atoms? It's worth noting that this way works. There is another way to solve this problem. You can actually rearrange these steps and get the same outcome. So we can start with the 2.3 moles of O2. Remember, you can use your molecular formula in moles. 1 mole of O2 gives you 2 moles O. And then you can step down, it's 6.022 times 10 to the 23rd O atoms for every 1 mole of O. This is the same idea in that I'm dealing with going from O2 to O first, and then I'm going from moles of O into O atoms. And as we'd expect, you can see I basically multiply 2.3 times 6.022 times 2. Here I just do 2.3, the 6.022 times 2. So I get the exact same answer out of it. I have to look that up again. (2.8) times 10 to the 4th O atoms. And we just rearranged it. We can use the fact the molecular formula, which we did on atoms and molecules up here, still works on moles, that we can do it right here. So we're using the same tools, just in a different order. So purpose of me telling you this is, both of these work, it doesn't matter, whichever one makes more sense to you works. The book talks about one and not the other, but both of them work. You may also find guidance online if you look up other resources where one or both of these, either format works, because really all that matters is the answer. Doesn't matter how you get it, and the fact that you're using those tools in whatever order you deem appropriate. Participation 6.8, question 2. How many carbon atoms are in 2.1 moles of glucose, which is C6H12O6? This is the second question on participation 6.8, due Monday, June 8th at 11:59 p.m. over on Blackboard. Link to the assignment is right below the links to these videos. Again, how many carbon atoms are in 2.1 moles of glucose, which is C6H12O6? All right, so we started this idea about counting and kind of dealing with numbers of atoms. That this motivation, we were going to do that when we were performing chemical reactions. We knew we had a lot, so we said it'd be like something like 100,000. That was a way undercount. Really, you're looking at something like 10 to the 24th atoms. Just huge, huge numbers of atoms. They are so small that when you're working with atoms, any sort of sample of matter, there are literally innumerable numbers of atoms in there. So there's a lot of atoms in there. That's not really, it's hard to even think of what that even looks like. So it's kind of meaningful to have a value that's this large. So instead, we count by groups. That's where the mole comes in. Right now, we're dealing with amounts. It's 1.7. That's an idea you can think about. You may not currently know what 1 mole of lead atoms looks like, But if we just kind of at least assume that 1 mole is about a reasonable amount, that's and the amount we're used to kind of dealing with, then we can at least say that 1.7, that's not a ton of lead. That's probably a reasonable amount of lead that we'd be working with. So we're efficiently counting atoms, kind of develop that sort of sense. But 10 to the 24th just feels big. It's hard to know, and it is a ton of atoms. But it's hard, since atoms are so small, it's hard to know, is that a reasonable amount of atoms? Is it not a lot of atoms? But when we convert into moles, now we can kind of wrap our head around that. 1.7 is at least a number that has makes some sense to us. So we still want to get into looking at mass, and we're going to need to answer the question of how does mass interact? What's the mass of a molecule? How do you go from atoms and molecules into grams of something? And that's something that will have to be left for another video. Okay, another question for participation 6-8. I think we're over halfway through this. Yeah, we're over halfway through the set of videos by number of videos, mostly by time. So I've got a couple more videos to go, but we're in the back half. See you in the next one.